Alrighty, so this video is going to be about the integrations involving inverse trig, kind of similar to the natural logs. We're not actually integrating inverse trig. We don't get that until Calculus BC, until the second semester. What we're doing is we're just reversing, or we're undoing, an inverse trig's derivative. So we're going to start off with the derivative and then work our way backwards and land with the inverse trig. So we're integrating into inverse trig. We're not actually integrating the inverse trig. Okay, so here we go. Before we get into the new notes for today, which again is mostly going to be pattern recognition. The better you know the derivatives, the easier the integrations are going to be. But before we get into those before we get into the integration rules, let's look at these three examples. We're going to look at the derivative of sine, the derivative sine inverse, the derivative of secant inverse, and the derivative of tan inverse. And we're going to take these derivatives and we're going to make them look nice and pretty. Yeah. To recap, let's kind of go through those derivative rules. If you have a sine inverse of something, your derivative would be 1 over the square root of 1 minus something squared. Whatever's inside would copy inside, and then if you need to do chain rule, you can either put the chain rule on the top, or if you wanted to, you could put it on the right. But there's your derivative of your sine inverse, and remember, if it was a cosine inverse, all you would need is the negative. Okay, and then let's do the next one. If I had a tangent inverse of something, and I was taking the derivative, it would be 1 over 1 plus something squared. There's your formula. Whatever's inside would copy inside. And then, of course, if you need to do chain rule, you would stick that chain rule derivative in the top. Or if you wanted to, instead of putting it on the top, you could put it on the right. And cotangent would be the same, but it would be the negative version of it. And then the ugliest one, the arcsecant, or the secant inverse of something. When you take the derivative, it's going to be 1 over, you have the absolute value of something, and then you have the square root of stuff squared minus 1. And whatever this stuff is, copies in here, and it copies in here. And then you put your chain rule derivative on the top, right? So those are your three derivative formulas, and then the cofunctions are the exact same, but you would just need the extra negative. So let's practice with these derivatives, and then we'll be able to work our way backwards and do the integrations. All right, so here we go. Sine inverse. We're going to take this derivative. So it's going to be 1 over the square root of 1 minus something squared. There's your formula for your sine inverse. And then whatever's inside would copy inside. And then you would need to do chain rule. The chain rule derivative of x over 2 is going to be 1/2. So here we go. I'm going to put this 1/2 in the top because of chain rule. So there's your derivative. Now that's wonderful. If it were to tell me, hey, integrate, and if it were to start off with the integration looking like this, then yes, it would work backwards, and you would just spit back to that original sine inverse of x over 2, right? But it's not going to give us integrations that begin like this. That's kind of ugly. They don't like having the fractions on the top, the fraction at the bottom. They would kind of rather just have one numerator and then one denominator, and you kind of just have one fraction overall without having these fractions within the fractions. So what we're going to do is we're going to algebraically simplify this, right? We're going to just make this answer look a little bit prettier, because when we see integrations, it's always going to start not with this. It's going to always start with the prettiest version of this. All right, so let's go through again. We're just going to simplify. First thing I'm going to do is, instead of this 1/2 on the top, I'm going to take this 2, move it to the bottom. So this would be the same thing as 1 over, then I have 2 square root, 1 minus, and I'm going to square all this stuff out. So I have x squared over 4. All right, so wonderful. Took that 1/2. Instead of the 1/2 on the top, it's a 2 on the bottom, and we squared that. Now, what we're going to do next is actually take this 2, and we're going to put it inside of the radical. Let's do a little bit of scratch work. Typically, we see something like, I guess, we could do the square root of 20. And I know the square root of 20, well, that would be the same thing as the square root of 4 times 5. 4 is the same thing as 2 times 2. So you could simplify this into 2 roots 5. You could take this 4 on the inside, and since it's a perfect square, you could bring it to the outside, and then it becomes the 2. Typically, we simplify. We take the complicated root, and we try to simplify it as far as possible. But since the square root of 20 is equal to 2 roots of 5, that means if for some reason, if I were to start here, I could also work my way backwards. Normally, we take stuff out of the radical, but if you were to start with something like this, with the radical 2 root of 5, if you had something on the outside and you wanted to put it in the radical, you could. What you'd have to remember, though, is when you take this 2 and when you put it inside of the radical, you would actually need to square it. When we had the 4 inside and we took it out, we applied the square root, right? We did the operation that square root symbol was telling us to do, right? The 4 on the inside becomes the 2 on the outside. When I take something out, I'm square rooting it. That means when I'm working backwards, if I had this 2 on the outside, I know it's going to be a 4 on the inside. So when I take this 2 and I put it in, I'm actually going to have to square it when I put it in. And then that would still end up giving you the square root of 20. We don't typically put stuff in the radical, but you can. If you take something out, you square root it. When you put something in the radical, you square it. So here we go. We want this to look a little bit nicer. We got rid of the fraction in the top by just moving the 2 to the bottom, but I want to get rid of this fraction in the square root. So let's take this 2 on the outside and let's put it on the inside. We're going to put that 2 in the radical, and this 2 on the outside is going to become a 4 on the inside. Oh, x squared. Missed the squared, didn't I? So we took the derivative. That was all the calculus. Now we're simplifying it. Took that 1/2, put it on the bottom. Then we're going to take that 2, put it on the inside. And now I'm going to take this 4, and I'm going to distribute. And I'm going to end up getting, let's see, we get 1 over 4 times 1. So we have the square root 4 minus. And then here, that 4, when you distribute, the 4 and the 4 are going to end up canceling perfectly. And I'm going to end up getting a much prettier version, right? Here was the derivative as we kind of just applied the derivative rule, right? 1 over the square root of 1 minus something squared, chain rule on the top. That's the derivative, and that's perfectly fine. And this is mathematically equivalent to this. Now this, I think the second one, definitely looks a little bit nicer. And what we have to recognize is that, hey, these are the exact same. So when I see questions that are going to tell me to integrate, and we're going to end up integrating into inverse trig, it's always going to start you with something like this. It's going to start you with the prettiest, kind of most cleaned up and most polished version of that derivative. If I saw the integration of something that looked like this, then yes, that would spit back to the inverse sign, no problem. And you'd probably recognize that really quick. But the problem is, hey, it's not going to look like this because it doesn't want the fractions within the fraction. Instead, I would need to recognize, hey, something like this is still going to integrate into a sine inverse. You just have to recognize what the individual components of that sine inverse are going to be. The square root of 4 is 2. The square root of x squared is x. And then here the constant was first minus the variable part. So that's the sine inverse. Let's do the same process for the secant inverse derivative and for the tan inverse derivative. All right, so we're going to take the derivative and then we're going to clean it up. So here we go, secant inverse. Let me move it up. Stay on the screen, Mr. Belt. Take it up. I got 1 over the absolute value, and I got the square root something squared minus 1. There's your formula for your secant inverse. I'm going to copy x over 3 here, x over 3 here, which means a chain rule. I'm going to need a 1/3 on the top. Now again, if I were to see an integration, and the integration looks like this, the integration of this would spit you back to secant inverse x over 3. But you're not going to see integrations that start off with a term looking like this. It's going to clean up quite a lot, and it's going to always start you with that cleaned up version. So let's go ahead and simplify this. Again, I'm going to take this 3, put it to the bottom. Come on, plan, you can do it. And then here, let's just simplify inside the radical. We have x squared over 9 minus 1. Now notice this 3 is going to cancel. So right now I've got 1 over, I still have the absolute value of x. Then I've got the square root of x squared over 9 minus 1. So So that 1/3 that was in the top, when I put that 3 on the bottom, it does kind of cancel one of the fractions in the denominator, but I still have this extra fraction, and I kind of would rather have it look like this, where there's just one layer on the top, one layer on the bottom. I kind of just want one fraction overall. I don't want fractions within the fraction. So we're going to do something, and we're going to try to make this look a little bit prettier, kind of like what we did on the previous example. In order to get rid of this fraction, right, on the inside, when I squared that out, it was an x squared over 4. In order to get rid of this, I needed another 4 inside, but that another 4 that was inside, right, it was already there for me, because the chain rule put that 1/2 on the top. That 1/2 is the same thing as the 2 on the bottom, and that 2, when I put it inside, becomes a 4, which completely killed all of the fractions. What's nice about the sine inverse is you didn't need anything extra. All you needed to make that look really nice, all you needed was that number that was already there because of the chain rule. Okay. Now, when I want to make this look nicer, right, if I want to somehow get rid of this 9, right, I'm going to need a 3 on the bottom. When I put this 3 inside of the radical, it's going to balloon up to a 9. But if I put this 3 in the bottom, you're changing the value of your expression. To keep it fair, we're going to also have to put this 3 on the top. Okay, so follow the process. I put this 3 on the bottom so that I can kill this fraction to make the denominator look nice. But since I put the 3 on the bottom, I have to keep it fair, and I need this extra 3 on the top. Okay, now let's take this 3, let's put it inside, still have the 3 on the top, and then I have that absolute value of x, and then when I take this 3 and put it inside, it's going to be x squared minus 9. Right? It's going to take that 3, put it inside, square. It's going to kill the fraction here. 1 times 9 is 9. And then this is what the cleanest version of that derivative could look like. And you're typically going to see integrations, not integrations like this. The integration, if you were to see it, right, it would be a secant inverse. That's wonderful, but you're going to see the integrations that always have the easier looking thing to begin with, right? And this would also integrate to your secant inverse of x over 3. What you need to remember for the secant inverse is that this numerator, right, for the sine inverse, it just had to be 1, because in order to make the denominator look all nice and pretty, you didn't need anything extra. But in order for the secant inverse, in order for this denominator to look nice, you needed that extra thing on the bottom, which means to keep it fair, I needed that extra thing on the top. So check it out for your integration. You're supposed to have this 3 right here. Okay, square root of 9 is 3. It's not a coincidence that that's a 3 and that's a 3. The square root of x squared, it's not a coincidence that that's an x, right? It's all this pattern recognition. The secant inverse needs that extra number on the top. Let's do the tangent inverse and then we'll hop into the notes. Okay, tangent inverse is 1 over 1 plus something squared. Put in that something, x over 5, chain rule, 1/5. Okay, so there's the derivative. Again, if you were to integrate something that looks like this, it would be tangent inverse of x over 5. However, you're not going to see things that start off looking like that. Let's clean it up. I'm going to take this 5, this 1/5 on the top, I'm going to take that 5 and put it on the bottom. So I have 1 over 5. Then I have 1 plus x squared over 25. So I took that chain rule part, I moved it to the bottom, and I'm going to distribute it. And I'm going to have 1 over, am I still on the screen? That's kind of surprising. I'm going to have 1 over 5 plus. Now this 5, it does not completely kill this fraction. It'll kind of reduce it, but you still have a fraction left over in the denominator. And we really don't want that to happen. We want it to be 1 layer on the top, 1 layer on the bottom. We don't want the fractions within the fractions. So just like the secant inverse, in order to make this tangent inverse look a little bit nicer, we're going to need another term in the denominator, right? I need another 5 to end up killing this denominator, to kill this fraction completely. Since I need this 5 in the bottom to make it look all nice and pretty, I also need one on the top to keep it balanced. And then I could end up with the derivative looking like this, 5 over 25 plus x squared. There's the nicest version of your derivative. This and this are mathematically equivalent. But whenever you see an integration problem, it's never going to start like this. It will always, 100% of the time, every single time on the AP exam, it will always start like this instead. These are mathematically equivalent, so they will both integrate into your tan inverse of x over 5. You just kind of have to recognize that these two things are the same. These are both the result of a tan inverse derivative. That's just the nicer, cleaned up version where you've gotten rid of all the fractions within the fraction. Square root of 25 is 5. Not a coincidence that that extra number that you need on the top is a 5. Square root of x squared is x. Okay, so important thing to remember. Why did the sine inverse end up with a 1 on the top? Why don't you need anything else? Because in order to take this denominator and in order to make it look all nice and pretty, all you needed to kill that fraction, all you needed was already there because of the chain rule, right? All the numbers you needed to get rid of all the fractions in the denominator was already there because of the chain rule. You didn't need anything extra. The secant inverse, you had that 3 from the chain rule when you move it to the bottom. That kind of helps. That gets rid of one of the fractions, but you still had another one. So you needed this extra number on the bottom to clean it up, which means I'm supposed to end up with that extra number on the top. Okay, same thing with the tangent inverse. When you do chain rule, you will have that number on the bottom, but that number on the bottom from the chain rule, I'm off the screen. So when you do chain rule, you have that 1/5, which means you do get this number on the bottom. That number helps some of the fractions in the bottom get cleaned up, but it doesn't completely get rid of all of the fractions, right? That kind of whittles away, but in order to completely get rid of all of the fractions, you needed an extra term, which means in the numerator, I'm also supposed to have that extra term. Secant inverse and the tan inverse. In order to make the denominators all pretty, you need that extra term. So I'm supposed to end up with this extra thing. Now, here's the question. If I was going to integrate, right, if I had something like this, and I was integrating, we know that would spit us back, right? If I was integrating, that would be tangent inverse. The square root of x squared is going to be x. The square root of 25 is 5, right? And then plus c. We know that the derivative of this is that. Therefore, the integration of that is this. But here's the question. What if that 5 was missing? What if I had something like this? 1 over 25 plus x squared. What if I'm supposed to have the 5 but it's not there? How could you account for it? Well, just like what we've seen kind of in the past with u substitution, to account for that number that was supposed to be there but was not, you could have a 1 over that number on your original function, and that would have made it cancel. Right? If the 5 was there like it's supposed to be, then it would integrate straight to the tan inverse as you would kind of prefer. But if that number is supposed to be there, right, that 5 is supposed to be there on the top, if it's not, it just means there was a 1 over that number on the original function. Kind of the same idea for your secant inverse. If I was going to integrate, and if I had the 3 on the top like I'm supposed to, then that would integrate directly back into the 1 secant inverse of x over 3. But if that 3 is supposed to be there, but was not, it just means you would have a 1 over 3 on your original, and that 1 over 3 would explain why that term in the derivative was missing. Okay, hopefully that makes sense. Let's get into the notes and let's do some examples. Here's the formulas. We don't really ever fuss with the negatives. If for some reason, well, I'll talk about that actually in a minute. I don't want to get on a tangent. Okay, so let's look at this. When I see something that looks like this form, where a is a constant, and then u is going to be the variable term. Doesn't always have to be x. Most of the time it will be something to do with x's, but it could be anything. But a is the constant term, u is the variable term. When I see something that fits this type of a form, right, it's going to look like this. That's a sine inverse derivatives. What's important is that the constant part comes first and then the variable part is second. Right, so when I see something that fits that form, I know it's going to integrate into an inverse sign. The square root of u goes to the top, the square root of the constant goes to the bottom, and of course the plus c. This is assuming we've already done u substitution, okay, and we've already done the du. If I were to see something that looks like this, where I have the 1 over the absolute value of stuff, and then you have the square root. The absolute value symbols probably won't be there, but you have this stuff on the outside of the radical, and then you have the variable part minus the constant part. When I see something that looks kind of like this form, I know that would be the result of a secant inverse derivative. So when I see something that looks like this, it's going to integrate into an inverse secant. But remember, the secant inverse, it wasn't supposed to have a 1 on the top. The sine inverse was, but the secant inverse was supposed to have some extra number. To account for the number that's supposed to be there but's not, you could just have a 1 over that number on your original. So here we go. Why does the secant inverse have this 1 over a? Because the derivative of secant inverse, you would end up with an a over all of that stuff, right? You'd have an a over u square root of a squared minus u squared. You're supposed to have an extra number here. If you're supposed to have it, but it's missing, you just have a 1 over that number on your original to have made it cancel. Okay, so when you see something that looks like this, if there's stuff outside of the radical, which may not always be there, sometimes it reduces away, but the order for the subtraction, right? Constant minus variable, that's your sine inverse order. Variable minus constant, the order for the subtraction will always distinguish between the sine inverse integrations and then the secant inverse integrations, right? So whenever I see something that fits this type of a formula, it's going to integrate into a secant inverse, and when you're missing the number, right? You're supposed to have some number here. If that number is missing, then you just have a 1 over that number on your original. And technically, you're supposed to put these absolute values, again, just to avoid any weird domain issues. When you're integrating from this into the secant inverse, put the absolute values just around the variable part. If you don't put it, it's really not the end of the world. Another important point that we'll kind of come back to later with one of the following examples, probably in the next video, is that the u's in this formula must match. Right? You've got to be able to fit the formula before you can use the formula. This term, right, the u that's getting squared, that u has to match the one that's on the outside, and we'll deal with kind of how you can kind of compensate for it when it doesn't match. But in order to use this formula, the u's must match. Okay, and then your tangent inverse, they're the nicest. There's no square root, and it's addition. So when you see something that looks like this, by the way, the order for that could be either way. Doesn't matter. U squared plus a squared or a squared plus u squared doesn't matter because of the commutative property. But when you see something that looks like this, it's going to integrate into an inverse tan. And just like the secant inverse, remember, you're supposed to have some extra number here on the top. And since you're supposed to have some number here, but it's missing, you just have a 1 over that number on the original function, which I've made it cancel. Okay, so important thing to remember, right? The order for the subtraction will tell you sine inverse or secant inverse. And then the sine inverse, that's the only one that does not need 1 over a. Right? The secant inverse has a 1 over a. The tan inverse has a 1 over a. The reason why sine inverse does not need a 1 over a is because in order to make that derivative look really nice, you didn't need to do anything. All the numbers that you needed were already there because of the chain rule, right? And the derivative naturally, by itself, will get to that 1 over the really nice denominator. But your secant inverse and your tangent inverse, remember, you're supposed to have this extra number on the bottom in order to make it look all pretty, which means I'm supposed to have this extra number on the top. If that 3 is supposed to be there, but it's not, a 1/3 on your original explains why it's not there. Okay, so when you're integrating something like this, remember the secant inverse and the tangent inverse, they need the 1 over a because in order to make the derivative look all nice and pretty, you're supposed to have that extra number on the top. I hope that makes sense. Conceptually, I think by the time, at least for the Calculus BC students, if you're seeing this the second year in a row, it should make sense. But overall, if you just have to remember, sine inverse does not have 1 over a. The other two do, as long as you can get these questions right. Conceptually, it's not the huge end of the world if you don't really understand cognitively why it is the way it is. You just got to be able to get the questions right when they come up. All right, so we're going to do some practice examples, and then we'll put it into this video, and then the harder questions will be on the next video. Okay, but these ones basically identify which inverse trig it's going to be, sine inverse, secant inverse, or tan inverse, and then after you know what form it is, you identify the u, and then check to see if anything's off with the u sub, and then you identify the a, and then you check to see if you need the 1 over a. right? It's pretty kind of simple once you know the patterns. They're ugly formulas or ugly patterns, but once you know them, the questions are actually fairly easy. Here we go. We've got the integration of 1 over the square root of 4 minus x squared dx. Okay, so I know this one must be a sine inverse. It's subtraction, and the constant's first. So I know this must be a sine inverse. I know the a is not 4. It'd be the square root of 4. So the a is 2, and then the u, the square root of x squared, is x. Since the u is x, that means the derivative du would be 1 dx, right? If the u is x, you don't have to worry about u sub because the derivative is just 1. You're good. So here we go. Does sine inverse need the 1 over a? No, it does not. And it's always u over a for the argument. Okay, so sorry, I'm going to get interrupted multiple times by the announcements really quickly. But it's always u over a inside of the inverse trig. So you basically identify which formula is it going to be? What's the u? What's the a? And then do I need anything for u sub, which in this case we didn't? And do I need the 1 over a out in front? And then, of course, don't forget the plus c. I'm going to wait until the announcements are done, and then hopefully we can do all the rest of the examples without having to pause. Okay, hopefully they're done. Should be. All right, so next one. Got to determine which inverse trig form. This one's easy. There's no square root, and it's addition. So we know that one is going to integrate with an arctan, or an inverse tan. Now let's think. The u value, right? No, it's not u substitution. It's weird that it's the same letter, but it's just the formula. The u value, the square root of u squared, would be just x. And if the du, if u is x, then that means du is just 1. So that's really lovely, right? Nothing's going to kick out because of the u substitution when your u is just x. Here my a value is not 9. The a value here is 3. So I'm going to have x over 3, that's the argument of the trig, and then the tan inverse needs the 1 over a. To account for this 3, remember, to make that tangent inverse derivative look nice, you're supposed to have an extra 3 on the top. Because it's not there, your original must have had a 1/3 to have made it cancel, right? Tan inverse and secant inverse, they need 1 over a. The sine inverse does not. I hope you understand why, but if not, it's okay. It should be able to do the questions anyways. Now, this is a definite integral. So we have to finish plugging some stuff in. I've got 1/3 tan inverse 3 over 3, that's just 1, minus 1/3 tan inverse root of 3 over 3. Okay, so let's finish this. Tangent inverse of 1, that's pi over 4. Now, root 3 over 3, that's the same thing as 1 over the root of 3. This is just the rationalized version of it. So if I want a tangent inverse of this, that's 1/2 over root 3 over 2. So the sine, the y-coordinate is 1/2. The cosine is this. So that's going to be your point, right? If your cosine is root 3 over 2 sine, that means you go over a lot, up a little. So that means this inverse tan is going to end up being a pi over 6. Inverse tans are a little bit ugly, but you should still be able to do them. That was kind of the whole point of pre-calculus. Anyways, here I got pi over 12 minus pi over 18. You could leave the answer like this, or if you wanted to combine it, the least common multiple between these two things would be 36. That's 3 over 36. That's 2 over 36. 3 minus 2 would be 1. So then this would end up being 1 pi over 36. Then there's nothing wrong with this if it's a free response, but if you wanted to get it down to one singular final answer, for a multiple choice, it would be the pi over 36. Alrighty, next one, secant inverse question. How do I know it's a secant inverse? A, most obvious, if it ever has something outside of the radical, it must be a secant inverse, because the sine inverse doesn't have stuff outside of square root. But also, what gives it away? The order for the subtraction. The variable part's first, constant part is subtracted from it. The order for the subtraction will always work. Don't bank on this always being there. Sometimes it will, sometimes it won't. So here I've got the u on the inside is x, and then the u on the outside is x. That's nice. Remember, the u's must match. Here they do. The derivative of u would be 1 dx. That's really nice. Nothing kicks out because of the u sub. The a is 5. So here we go. This one's going to integrate into your inverse secant. And then we have u over a, x over 5, absolute value of x. And the secant inverse needs the 1 over a out in front. Okay, so these inverse trig integrations are a little bit annoying, but kind of once you get the process down, they're really okay. right? You just got to figure out which inverse trig formula it is, what's the u part of the formula, and does anything kick out because of the u sub? Nothing has yet, but it's going to in a couple of examples. What's the a part of the formula, and does a 1 over a kick out because of the formula? Right, and then we just kind of bring it all together. U over a is inside, or the absolute value for the secant. All right, let's look at these three because they're similar. Here's 4 over x squared plus 9. This is 4x over x squared plus 9, and then this is 4x squared over x squared plus 9. Only one of these three questions is going to involve I guess the kind of a u substitution. One of them is going to involve the inverse trig right away, and then one of them we're going to have to do some extra algebra before we could potentially even try to integrate it. Let's try to find the u sub one first. Okay, so if I were to, by the way, you should always try to do u sub. For this first example, right, if you tried to set the u as 4 minus x squared, if this was your u, then your derivative would be negative 2x. You don't have the negative 2x. You don't care about the negative. You don't really care about the 2. But if your u is quadratic, you would need an extra x. Now, I need the x to be on the top. Since it's not there, u sub doesn't work. Same thing here. If you try to set this as your u, the derivative would be 2x. You don't really care about the 2 missing, but you do care about the x, right? If your u is quadratic, you would need the x. Here, your u is quadratic. If you tried to do it, you do have the extra x, but that x would need to be on the top for u substitution to work. Okay, the derivative of this would not put an x on the bottom. So u substitution doesn't work for any of the first three. That's why I just did them with the inverse trig. But sometimes u sub will work for a couple of these, right? Just because we're learning inverse trig doesn't mean you use inverse trig on every single question. Sometimes regular old u sub is going to work. So let's look. Here, if I tried to set u as x squared plus 9, the derivative would be 2x. Nope. Here, if I set it as x squared plus 9, oh, there's the x. You don't have the 2, but that's okay. Here, it's quadratic on both layers. So this is the one that's going to end up being just u sub. Since it's quadratic on the bottom and linear on top, u sub's going to work. This one is going to end up being an inverse tan right off the bat. Since it's quadratic on the bottom and you're missing the x, those are the ones that end up integrating into an inverse tan. Let's do the u sub first. U equals x squared plus 9. So then your derivative would be 2x dx. It's supposed to be a 2, but it gets made into a 4. Right? So the derivative tells you what that number is supposed to be. Then you compare what it's supposed to be to what it actually is, and we're like, okay, a 2 is going to end up kicking out. So a 2, then I have 1 over u du. So I set the denominator as u. All of this stuff on the top, 4x dx, that's equal to 2 du, and then I have the integration of 1 over u, which integrates into ln of u, plus c. Thank goodness this is an indefinite integral. And then we have 2 ln x squared plus 9 plus c. So there we have it. That one didn't involve an inverse trig at all. It was just a u sub, and then it ended up using a natural log. Okay, now let's go back and let's do the previous one. Here it would be an inverse tan. I know it because it's addition and because there's no square root. The u for the inverse tan would be just x. It's the square root of the variable part. The a for your inverse tan, not 9, the a would be 3. Okay, so let's check. If u is x, that means du would be 1 dx, so nothing's going to kick out because of the u sub. How lovely. So let's go for it. The 4 I'm going to just copy. The 4 is just there. And then all of this stuff, we know it would be tangent inverse u over a, so it's going to be x over 3, and then tangent inverse needs the 1 over a plus c. Then if you wanted to recombine it, remember that 4 was just kind of extra. That 4 had nothing to do with the integration. You can just bring it out to the front, but then you could recombine it at the end. 4/3 tan inverse x over 3 plus c. So that one we used the tan inverse right off the bat. This one used the u sub right off the bat. And then the last one, It doesn't fit for inverse tan right off the bat because you got these extra x's on the top. It also doesn't fit u sub right at the bat because you have two x's on the top. What you need to do, if the top is the same degree as the bottom, or if this was cubed, if the top is bigger than the bottom, or if the top is the same degree as the bottom, what you need to do is division first to rewrite it and to simplify it, to break it up, and then after you do the division, then you could go through and integrate. So I'm going to do long division. Synthetic division will not work since this is a quadratic divisor, so you'd have to do long division. So here we go, 4x squared plus 0x plus 0. I'm going to divide it by x squared plus 0x plus 9. This goes into this 4 times. 4 times this is 4x squared. 4 times 0 is 0x. 4 times 9 would be 36. Parentheses first. Then you could subtract. Those are going to cancel. Those will also cancel 0 minus 36. So here we go. Doing long division, I could just split this thing up. And then I would have 4 minus, you have the remainder of 36 over your divisor, x squared plus 9. So when the top is bigger than the bottom, or if the top is the same as the bottom, you can do the division first. Long division, probably. Sometimes you can do synthetic, but only if it's linear. Those typically only come up with natural logs. This is going to end up being an inverse tan. Right? The 4 has nothing to do with the inverse tan. The 4 is just going to integrate into 4x. But this part right here, that one's the one that will end up being an inverse tan. The u of your inverse tan would be x, which means your u substitution is going to be fine. It's just dx. And then the a is going to be 3. So here, let's check it out. The integration of 4 is 4x. And then minus, I'm just going to copy the 36. You'd have the 1 over a. So I'm going to put the 3 on the bottom. That's your 1 over a. Tangent inverse u over a plus c. And then if you wanted to, you could reduce that. That's just going to be a 12. So 4x minus 12 tan inverse x over 3 plus c. So those 3 examples looked pretty similar, but one of them, they were all 3 done very differently. One of them was u sub right off the bat, and then one of them was an inverse trig right off the bat, and then one of them you actually had to do the algebra first. You had to do the division first, and then part of it was really easy, and it was just the remainder over the divisor piece. That one will either integrate with a natural log if it's linear, or if it's not linear, hopefully it'll integrate with an inverse tan. Okay, so there we go. So those integrations, again, there's just pattern recognition. Once you are really good with the pattern, these ones really aren't too bad. In fact, they're kind of fun, I think, but they can be challenging for sure at first. Let's do a couple more. Let's do I'm going to do one more example, and then I'll probably make up another example or 2 just to kind of drive home a point. But we'll do these ones probably in the next video because those ones are going to be a little bit more complicated. Can't hold my pencil. So we'll do those ones in the next example. And I think the next page, the next page is just review, so we don't even care. Let's do this one, though, and then I'm going to make up another one for us to do afterwards. Okay, here we go. So looking at this integration, first thing you have to do is decide which inverse trig formula is it going to be. Why won't it zoom in? Oh my gosh. Will it zoom out? Nope. Okay, well, sorry, that's as good as it's going to be. So I'm looking at this, and I see I've got 1 over square root of 4 minus x squared. Ooh, here we go. The constants first, then you subtract the variable part. So that one's going to end up being a sine inverse. And I know the u part, the square root of 25x squared, the u part would be 5x. This is the first one that we're going to have something kick out because of the u sub. If u is 5x, the derivative should be 5 dx. You're missing the 5. Okay, so this 1/5 is going to end up kicking out because of the u substitution. Now let's look at the a value. It's not 4. The a value would be 2. So now I'm ready, right? Kind of got all the parts for this formula. Let's use the formula. It's going to end up being a sine inverse. You can do arc sine if you want. I just like sine inverse. It's going to be u over a, so 5x over 2 is indefinite, so put plus c. I do not need a 1 over 2 because sine inverse never, ever, ever needs the 1 over a. But I do need the 1/5. The 1/5 is not the 1 over a, and that 1/5 is there because of the u sub. Okay, let's do probably 2 more examples. Let me make these up. Let's do this one. How about x dx over 81 plus 64 x to the 4th. Again, u sub for a whole wouldn't work for this. If you tried to set all of this as u, you would need an x on the top for the u sub to all fit together and to work. Similarly, if I tried to set all of this as u, right, if my u was a 4th degree term, I would want this to be x cubed. If that was an x cubed on the top, it would just be a simple u sub you would integrate with the natural log because you'd have a 1 over u. You may have some coefficient because it may not match perfectly, but if the bottom was to the 4th and the top was to the 3rd, u sub for the whole thing is how it would work. Since it's not that way, we're going to try to see if we can somehow get an inverse tan to work. I know it's inverse tan because there's no radical in its addition. Let's see. 81 plus, let's see if we can write this as something squared, because I always want something squared plus something squared, right? We got to have it as a specific form in order to fit the inverse trig formula. Square root of 64 would be 8. The square root of x to the 4th would be x squared. So you could rewrite 64x to the 4th as 8x squared, in parentheses, squared. And then this one, you could use the u substitution within the inverse trig. Here your u would be 8x squared. And then the derivative of 8x squared would be 16x dx. Now, you don't have the 16. That's okay. You do have the x, though. So here, a 1/16 is going to kick out. Not because of the 1 over a. The 1/16 is going to kick out because of the u sub. The a value here, the square root of 81, the a value is 9. So when I integrate this, I'll do it down below, you have the 1 over 16, which kicks out because of the u sub. You also have a 1 over 9 that kicks out because of the 1 over a. And then we'd have this tangent inverse u over a. So we'd have 8x squared over 9, plus c. And then we could just combine all this stuff. Sometimes you have one number that kicks out. Sometimes that number kicks out because u sub, or other times, as we saw in the previous example, sometimes you have a number that kicks out because of the formula, the 1 over a. Sometimes for the tangent or the secant inverse, you may have 2 numbers that kick out, right? And then you would just kick out the thing from the u sub, kick out the thing from the 1 over a, and then you could just combine them. 16 times 9 would be 144. So this answer, you could rewrite it as 1 over 144. Tangent inverse 8x squared over 9 plus c. So the general process for questions like this is you identify the which inverse trig, right? Sine inverse, secant inverse, tan inverse. Then I identify the u, and I check to see if anything kicks out from the u sub. Sometimes it will. Even for the sine inverse, sometimes something may kick out because of the u substitution. You will never have a 1 over a for the sine inverse, but you could still have something kick out because of the u sub. So I identify the form, then I identify the u part of the form, and I check, does anything kick out from u sub? Then I identify the a, and then I check, do I need a 1 over a? Sometimes you have both, just recombine them. Okay, one more example. And then we'll end this video, and then we'll do the harder questions next time. I'm like, harder questions, Mr. Oh my God. Yes, the next ones are going to be harder. These ones are all just pattern recognition. Once you're good with the pattern, they're actually not too bad. A lot of algebra, but not too bad. Let's do one more example, and then we'll break. Let's do this. Integration, let's put dx on the top, and then let's put x, and then let's do, how about 16x squared minus 9. So let's see, I've got an integration like this, which we can tell right off the bat it's not going to work for u sub. Because if I tried to set all this as u, I would want an x, but I would want that x to be on the top, right? If that x was on the top, u sub would work, and then you could use your power rule. Since the x is on the bottom, it's not going to work. But it does look kind of like a secant inverse. When you have this extra stuff out on the outside, it does look like a secant inverse. Let's see if we can fit the formula. This would be 4x quantity squared. Now, the u in your formulas must match, right? So this is a 4x. Right now, that's only an x. 4x and 4, I don't know, or 4x and x, those aren't the same, okay? And in order to use the formula, let me flip it back over. in order to use this formula, when you have the integration of 1 over u and then the square root of u squared minus a squared, those u's must match. The thing in the parentheses that's getting squared, that u must match the one that's on the outside. If they don't match, you need to make them match before you can use the formula. So check it out. This is a little bit of witchcraft, okay? But this is how you go through and you can do these kind of weirder, harder secant inverse ones. That is not a liar. That is always 100% of the time, every single time. That is always going to be the u, right? So the u is 4x. Now, this one may be a liar, because that one may have reduced with something, right? Nothing's going to fuss with the stuff inside the radical. This one may have reduced. So what I would do is I would figure out what's the u from this term, and then if this does not match, I'm going to make it match. Okay, so since I know that's a 4x, this must also be 4x. But if I put that 4 on the bottom, you're changing the value of your expression. So I'm putting this 4 on the bottom to make the u's match. And then to keep this equation balanced, I'm going to also put a 4 on the top. Okay, so these secant inverse ones, the u's must match. If they don't, make it match. But if you make it match, keep the equation balanced by putting that same thing. Then once you do that, then you can go through and you can check your u sub. Your u is 4x. So the derivative is 4 dx, and look, that is exactly what I have. Initially, if you try to visualize it without the things in red being there, initially, when you see the 4x, it looks like you were missing something. So it looks like a 1/4 was going to kick out because of the u sub. But really, that 4 was there. It had just reduced with the other one. So you got to be careful. If it's a secant inverse, you identify the u, you find out, you see if the u's don't match, you make it match, identify the u, make it match, and then if you have to make it match, you keep the equation balanced, and then after you've done all those things, after you've jumped through those hoops, then you check, does my u sub match, or does my u sub appear to still be off by some constant? It still may be off by a constant, but you have to do some work first before you check. Okay, so make the u's match, then keep the equation balanced, then we can go through and do this integration. The a would be 3. So let's integrate this. It's going to be a secant inverse. It's going to be u over a. So it's going to be 4x over 3. And then this one does not need anything because of u sub. It kind of looked like it was missing the 4. It was there. It had just been reduced. But you do need the 1 over 3 because secant inverse needs the 1 over a. Okay, so just be careful. Got to make the u's match first. Then you make the u's match. Then you keep the expression balanced. Then after you've done that, then you compare this with your u sub to see if anything's off by a constant. What I would really, really strongly recommend is for you guys to practice some more with this stuff, because these inverse trig derivatives and these inverse trig integrals, they're just weird. They're weird, ugly formulas. Once you know the formulas, they're honestly not too nasty. The ones next time will be a little bit nasty, but it's nasty because of the extra algebra we have to do. The calculus is just pattern recognition. What's the u? Does anything kick out because of the u sub? What's the a? Do I need a 1 over a? And then you just kind of plug and chug into the formulaic process. What I would recommend that you guys do is just practice. Now, in order to give you some extra practice, typically, if this was a regular year, which you may be watching this in a regular year, typically we would have warm-ups, and you're probably sick of doing warm-ups, but usually I would strongly recommend that you go and do these warm-ups. Okay, now you can find the warm-ups on my website, and then the answer keys for the warm-ups. Most of them are on that same page, but everything for the warm-ups is on my website. I'm going to try to just put this under the screen, and then if you're too lazy to go to my website and to actually find the warm-up folder and to go find the one that says practice with inverse trig derivatives, then you can just go ahead and pause the video right now. You can do it. Pause the video, and then you can just take a picture of this or write these questions down, but I would suggest you practice with these derivatives. Here's 8 questions with these inverse trig derivatives, and then pause it. Right, here's your chance. Pause it, copy them down, and then there are the answers for them. Again, pause it, copy them down. The answers they're all on my website, right? Go to my website, click on the little link, I think it says warm-ups, and then you just have to navigate to it. This is the one that says practice with inverse trig derivatives. The derivatives are fairly important for you to practice, but really what's more important is going to be the integrals. Okay, so here, I actually kind of put that right on the screen right away. So here's the other warm-up that says practice with inverse trig integrals, and it's 12 questions. I'm trying to see, everything looks fairly visible on my screen, so I hope it's legible for you. I would say really practice with these because the pattern recognition is going to really increase your speed and it's going to increase your confidence level when you do these. Like which ones are sine inverse, which ones are the tangent inverse, which ones are the secant inverse. Gotta just be really careful. The secant inverse, some of the ones that look like they're going to be missing something because of the U sub, some of those actually match perfectly. The ones that actually look like they're going to match perfectly, sometimes they're actually having too much. They have that extra number, and then sometimes you will actually be missing and you'll kick out the 1/5. But I would pause, and I would definitely recommend that you do these 12. And then if you do the homework's kind of got a mix of like a couple of easy questions, but mostly it's got some of the practice questions that are a little bit harder that we're going to cover with the next video. But I would just really grind out a lot of practice reps with these easier ones, especially the secant inverse ones. Make the U's match first, then you keep the expression balanced, then you check to see if anything kicks out because the U sub. Sometimes the looks can be deceiving. I would do these, and then I would check your answers to make sure that you're doing everything right. Those are a little bit harder to see, so you may want to go to my website and look at the practice with inverse trig integrals. Pull up the PDF file, but it's there for you. You can find it through my website. Okay, so practice with the inverse trig derivatives. You have those 8 questions. Those are probably pretty nice. Typically, though, the derivatives aren't the things students have the most trouble with. It's the integration ones that are a little bit harder. So you have the practice with the integrals. And then this is not for a grade, right? So you do not have to do these. I'm just giving you extra resources so that you have them at your disposal if you choose to do them. But you have the practice with the inverse trig derivatives and then the practice with the inverse trig integrals. But wait, Billy Mays here. But wait, there's more. I have some more, right? I got another warm-up. I know it's very uncreative with how it's named. The next warm-up is just called more practice with inverse trig derivatives. Very unoriginal. Again, pause the video, copy them down, or pause the video, take a little screenshot, and then you can go ahead and check your answers. And get them on the screen. There you have it. Again, you can pause the video. That's what's nice about making videos. You can literally pause it. I don't have to waste my time waiting for everyone in class to get them. Okay, but there you have it. There's more practice with the derivatives. And yes, of course, there's another one. Of course, there's a more practice with the integrals, another 12 questions. If you were to do these 4 optional warm-ups, the practice with the derivatives, the practice with the integrals, the more practice with the derivatives, the more practice with the integrals, if you were to do all 17 million of these questions, and if you were to get all the practice with these inverse trig stuff, then you're going to be fine, right? The stuff with the inverse trig, the more practice you get, you'll really figure out, okay, it really is just pattern recognition. Once you know those ugly formulas and you can kind of go through those process, what's the inverse trig? What's the U part of the inverse trig? And then does anything kick out because of the U sub? What's the A part of the inverse trig formula? And does a 1 over A kick out to the front? And then it's just very kind of plugging and chugging. It's very kind of repetitive. But there's your more practice with your inverse trig integrals. And then there you have the answers. That one's a little bit harder to see. Remember, all these PDFs of the warm-ups, you can find them by going to my website, click on the little link that says warm-ups, then you just find the ones that say practice with inverse trig derivatives, practice with inverse trig integrals, more practice with the derivatives, more practice with the integrals. If you want the practice, there's definitely stuff available to you. The integrals in particular, especially ones like this, which are the secant inverse, those are just tricky, so I would strongly suggest that you do them. In the next video, we'll go through and we'll do some of these harder questions, but also we'll hopefully be able to do most of those in class the next time I see you. All right, so that's a wrap. I know this video was really long. Hopefully it was worth it.